So with this video, what I want to do is introduce you to the idea of blood pressure and then talk a little bit about how to calculate what's known as the mean arterial pressure, which is really kind of the average blood pressure in a vessel. So I've got a diagram over here that kind of represents what blood pressure is. Basically, blood pressure is the force that is applied to blood vessel walls by the blood that's contained within it. So if you look at this little vessel here, we've got a portion of the wall removed so that we can see inside. And we've got some blood, which is cells and fluid contained within this blood vessel. And that fluid, the blood in the cells, is putting a pressure. It's applying a stretch, basically, or a force to the blood pressure or to the blood vessel wall. And when we're measuring blood pressure, that force, that stretch, that pressure that's put on the blood vessel wall is what we're actually measuring. So I know a lot of students come into this class with some background in medicine, but I want to make sure that we're all kind of on the same page with what blood pressure is. And so I want to talk a little bit more just from kind of a background baseline information as far as blood pressure is concerned. So you may have heard it said that an average healthy blood pressure for the systemic circuit is 120/80 or less as measured in the brachial artery. So there's a couple of things there that I want to talk about. So first of all, anytime we've got a blood pressure in a vessel, we actually get two numbers. The first number is the higher number, so this 120 is our first number, and that's always going to be your systolic pressure. So the systolic pressure is the higher number because it's the higher pressure. The systolic pressure occurs in a blood vessel when the heart is contracting and it's actively pushing blood into the vessels. And of course, if the heart is contracting with a lot of force and it's actively pushing blood into the vessels, we're going to expect the pressure in those vessels to be higher than what we would see when the heart is relaxing and blood isn't actively being pushed into the vessel. The second number, the lower number, so in this case it's 80, is what's known as the diastolic pressure. And the diastolic pressure is the pressure being placed on the vessels when the heart is relaxed or when the heart is in diastole. This pressure, of course, is going to be much lower because the heart isn't actively contracting at that point and pushing blood into the vessels. However, we do see a pressure during this time, and one of the reasons for a pressure in the blood vessels, even when the heart isn't contracting, is because remember that especially arteries have a lot of elastic to their walls, and when the heart contracts, it forces blood very forcefully into these vessels and they expand. And then when the heart relaxes, these vessels recoil back down. So as the vessels are recoiling back down, they're getting some pressure from the blood that's contained within them, and that's what's actually causing that diastolic pressure. So we have a systolic pressure, that's the higher pressure. Again, it's when the heart is actively contracting. Your second number, your lower number, is the diastolic pressure. This is the pressure in the vessels when the heart is relaxed. But we do have a pressure during that time, primarily due to the recoil of vessels, and that's really important that we do have a pressure because that ensures that blood keeps moving through the vessels of the body continuously. If that wasn't the case, we'd have blood flow as the heart was contracting and generating pressure, and then that blood flow would stop when the heart relaxes until it contracts again. Having a systolic pressure and a pressure in the vessels during diastole ensures that we get a continuous movement of blood throughout the body. The other thing that I want to point out is that when we talk about this 120/80 being the normal healthy pressure, that is as measured in the brachial artery. So the brachial artery is in your upper arm, and that's why blood pressure cuffs are always placed on the brachial artery because that's where we're measuring the blood pressure. One thing that you should know about blood is it always moves from areas of higher pressure to areas of lower pressure. So 120/80 is normal and healthy in the brachial artery. If you were to take the blood pressure in an artery that is further from the heart than the brachial artery, say the radial artery down in the area of the wrist, a normal healthy pressure in that area would be less than 120 over 80 because it's further from the heart and the pressure should have dropped by that point in order to be considered healthy. If you had a radial pressure that was 120 over 80, that would be too high because blood always moves from higher pressure to lower pressure, and if it's 120 over 80 in the radial artery, that means that the pressure is going to be even higher in the brachial artery. And because blood is always moving from areas of higher pressure to areas of lower pressure, if you were by chance measuring blood pressure in an artery that's closer to the heart than the brachial artery, and there's not a lot of those, but if you were, you would expect a normal healthy blood pressure to be higher than 120 over 80. Again, just because blood always has to move from areas of higher pressure to areas of lower pressure. So we've kind of addressed this idea that the pressure in the vessels of the body, at least in the arteries, is fluctuating. It's higher when the heart is contracting during systole and actively pushing blood into these arteries. It's a little bit lower when the heart is relaxed during diastole and we don't have blood flowing from the heart into the arteries. So we've got this fluctuation whereby it's higher and then it's lower and then it goes back up to higher and goes back down to lower. And basically that's happening with each heartbeat in the body. Because of this, because we've got this fluctuation going on, we calculate what's known as the mean arterial pressure or the MAP to get kind of an average pressure in a blood vessel. One of the reasons for this is if we're able to calculate the MAP or the average blood pressure, that's going to allow us to know how much pressure is in the vessel driving blood to the tissues of the body. Because if there's not enough pressure, if the MAP is too low, now we're going to start to have problems actually with blood flow to tissues and organs getting what they need. If the MAP is too high, now we're going to have problems with damage to blood vessels, which can lead to heart attacks, strokes, clots, those kinds of things. So there is a range in which we want blood pressure to be within each of the different blood vessel types. And we can calculate the average pressure, which accounts for the fluctuations that happen by calculating what's known as the mean arterial pressure or the MAP. So down here, I have an equation for calculating MAP. Basically, MAP is equal to the diastolic pressure plus what's known as the pulse pressure divided by 3. Down here, I've given you a definition for what the pulse pressure is. So pulse pressure effectively is systolic pressure minus diastolic pressure. So if I were to give you a normal healthy blood pressure as measured in the brachial artery of 120 over 80, you could really quickly, easily calculate the MAP for that vessel by plugging in the diastolic pressure, which would be 80 in this case, right? Because we're working with a blood pressure of 120 over 80 as measured in the brachial artery. So 80 is our diastolic pressure. Our pulse pressure is our systolic minus our diastolic. So 120 minus 80 is 40. That's our pulse pressure. And then we divide that pulse pressure by 3, and that makes this 40 actually 13.3. And then we just add 80 plus 13.3, and that gives us a MAP when our blood pressure is 120 over 80 of 93.3. That would be the average pressure in the brachial artery that would be driving blood flow to tissues downstream. Now you may be looking at this number, this 93.3, and saying that's not a pure average, right? Because if we took a pure average, we would do 120 plus 80, which would give us 200, and then we would divide that by 2, and that would give us an arterial average pressure of 100. The reason that this number is smaller, it's closer to the diastolic pressure, is because the heart is actually in diastole, usually, and this can change somewhat based on heart rate, but usually about 3 times as long as it's in systole. Because it spends much more time in diastole, we need to account for that in our equation that we're using to calculate the average pressure. And we do that through this pulse pressure portion of this divided by 3, and that's going to give us a lower number than 100. So the average pressure is closer to the diastolic pressure than it is to the systolic pressure. And again, that simply has to do with the fact that our heart spends more time in diastole, significantly more than it does in systole, and we've got to account for that. So I want to give you a chance to work with another one. Let's say that somebody has terribly high blood pressure, and their blood pressure is actually 160 over 120. What I want you to do is go ahead and work with this MAP equation and calculate what the mean arterial pressure would be when blood pressure is that high, and then also calculate what the mean arterial pressure would be when you've got a pressure of 60 over 40. Okay, so a really, really low blood pressure. So if you need to, go ahead and push pause on this particular video and work through those calculations so that you're familiar with how to calculate MAP. So the first one we used was 160 over 120. I'm going to go ahead and work through that one with you. In that particular case, our diastolic pressure is 120, right? And our pulse pressure is going to be 160 minus 120, which once again is 40. And when we divide 40 by 3, that's giving us that 13.3 number again. And when we take 120 and add to it 13.3, we come up with an average pressure of 133.3 when blood pressure is high. So that's just giving you another example of how you would go ahead and calculate the mean arterial pressure. And when blood pressure is high, when you're hypertensive, now the pressure in the arteries is high and in all the other vessels as well, and that can be really damaging to the tissues of the body. The second example that I gave you to calculate was when the blood pressure is too low. And in that particular scenario, now sometimes we don't have enough pressure in the vessels themselves to be able to continue to push blood towards the tissues of the body, which is also damaging. So there's a certain range in which we need to keep blood pressure in order to keep the blood vessels themselves healthy and the tissues that are fed by the blood vessels healthy as well. So here's our last slide with this particular lecture. And what I want to draw your attention to for just a minute is this diagram that I have over here, because you're going to be working with a similar diagram in the activity that you do. So I want you to notice that on the y-axis we have blood pressure, and blood pressure is measured in the units of millimeters of mercury. And on the x-axis we have the different types of blood vessels in order from the heart. So the first vessel that blood comes to as it leaves the heart is the aorta. From there, it branches out into various arteries and then into arterioles, which feed into capillaries. Capillaries feed into venules, which feed into veins, and the last veins are the vena cava, which are actually returning blood to the heart. So we've got the different types of vessels listed basically in sequence from those closest to the heart to those that are furthest away in the systemic circulation. And there's a few trends that I want you to notice as you look at this graph. So the first thing you may notice if you look at this graph, here's our systolic pressure. Okay, that's our upper number. This is our diastolic pressure down here. And this is our mean arterial pressure. Okay, what we would calculate for normal healthy blood pressure in each of these different vessel types. You'll notice the mean arterial pressure, or the MAP, is closer, again, to that diastolic pressure as I mentioned before. It's further away from the systolic pressure. And that has to do with the fact that, again, the heart is spending more time in diastole than it is in systole. Here's our pulse pressure. So remember that pulse pressure is the difference between the systolic pressure and the diastolic pressure. And you'll notice in the aorta that there's a big difference between those two. There's a big pulse pressure. As we move into the arteries and especially down into the arterioles, pulse pressure becomes less and less. So there's less and less of a difference between systolic pressure and diastolic pressure as we move away from the heart. Once we get down here to the capillaries and on through the veins, there's no difference whatsoever between the systolic pressure and the diastolic pressure. So the pulse pressure in these particular types of vessels is effectively zero. When you take somebody's pulse, when you feel that blood vessel kind of expanding out with contraction of the heart and then recoiling back down, you're actually feeling the difference between systolic and diastolic pressure. You're feeling the pulse pressure. You cannot take a pulse from a capillary or a vein because they do not pulsate. And the reason that they do not pulsate is there is no difference between systolic pressure and diastolic pressure in these particular vessel types. Another thing that I want you to focus on is this idea that blood is always moving from areas of higher pressure to areas of lower pressure. So we'll focus just on the map here. And you'll notice that as blood moves away from the heart, the mean arterial pressure, the average pressure, declines. So our pressure is highest in the arteries and it's lowest in the veins. It's actually lower in the veins than it is in the capillaries. And that's because when we're talking about the systemic circuit and the pathway that blood takes, blood moves from arteries to capillaries into veins before it returns back to the heart. And if blood's moving from areas of higher pressure to areas of lower pressure, then we've got to have a higher pressure in the arteries, a lower pressure in the capillaries, and a lowest pressure of all within the veins. So those are just a few trends that you can take from this particular graph that you'll be working with in the activity that you do for this particular folder.